Okay, Allie's here. We're going to see if we can actually use this one. There'll be one episode where we don't just have her on the blooper reel. All right, she's actually on the reel. Electrophillic addition is the next type of mechanism we want to talk about. And remember, these are going to get progressively harder because one of the reasons they get harder is that you're going to actually get them mixed up. So you have to be able to tell what's going on. This is an addition reaction, which is different from a substitution reaction. We're going to see another kind of substitution reaction tomorrow. Actually, that's not true. Tomorrow we're going to be doing that worksheet and computer thing. So electrophilic addition basically is an addition reaction across a double bond, an alkene, I should say. And it explains some things. In particular, it explains Markovnikov's rule. Remember Markovnikov's rule? Remember how whenever you added a bromine or an OH or something, it always went more towards the middle? Remember that? Yeah. You had to remember that because I yelled at you about it every time you put it on the end. You couldn't have a primary alcohol produced that way. All right? Well, this mechanism is going to explain why that happens. And this is a two-step mechanism. Not as many steps, but I need to go into a little bit of detail about what's going on. Now, I'm going to first show you a little video clip. Again, it's only 2 minutes long. It's an animation explain to you what's going on overall. Try to watch this, try to pay attention to it, all right, and I will then break it down into the individual steps and the notes you need to know for it. All right, but this is just the overall thing. So hit that back light for me. Great music, too.
Electrophilic addition involves two reactants. An alkene, whose double bond is rich in electrons and is thus nucleophilic. And an electrophile that will attack pi bond electrons in the alkene double bond.
A lot of new words
We'll
in
use
here.
hydrogen bromide as an example. Ultimately, they will react to form an alkane. This reaction takes place in two steps and is exergonic overall.
What does that mean?
So what are the
Energy
mechanisms?
is release. Exothermic?
One reactant is a potential electrophile. Because the bromine atom is electronegative and attracts electrons, it causes a partial positive charge on the hydrogen atom to which it is bonded. The hydrogen is thus electrophilic. Remember that a double bond contains one sigma bond and a weaker pi bond. Weaker because their orbitals do not overlap. These pi electrons are thus attracted to the partially positive hydrogen atom in the halide molecule and are able to form a stronger sigma bond. Because an electron has been removed from the adjacent carbon atom, the carbon atom becomes positively charged. This is called a carbocation. Meanwhile, this hydrogen has one too many bonds, and a pair of electrons transfers to the bromine atom to form a bromide ion. This is the first and slowest step of the electrophilic addition reaction. This step gives rise to a carbocation intermediate as well as a bromide anion. The bromide ion is now a suitable electron donor for the carbocation. The molecule is neutralized and an alkane results as the final product. This concludes the last and faster step of the reaction.
All right.
And that helped us out.
We got a lot from
Exactly. That's exactly why I showed it to you. It's exactly why I showed it to you. You guys look at that, and even though virtually everything in there, with the he used, oh my God, he talked about sigma versus pi bonds, which I did not do. All right, everything in there you already knew. You knew about from last year. Electronegative elements, bromine pulling harder, having a slight negative charge, slight positive charge. All right, you know what a double bond is. There's more electrons there. You know, you've seen that exact reaction as an overall reaction. Hit that backlight for me. But when you see it presented like that, and this is how many of you had Rothery, for example?
Oh.
All right. Remember when she would show you? I thought he was fantastic. He would show you that guy, right? Well, the problem with showing that first, like I just did here, and it's the same thing I'm doing here, is that you're watching it, and it's like there's so much. It's like an overload of information. Now, what I did when I showed him, I showed you a couple of those same ones that you probably saw with her, and I showed them after reviewing when we were doing. Remember when we were doing it for the Keystone review, and they made more sense. Why? Because you'd already been taught it, and that's exactly what happens. The information overload. You hear the word sigma, pi bond, electrophilic. You hear electrophile, carbocation, and you lose sight of the big picture. Now, when I'm done teaching this, and I have 2 other little animations that are part of it. I did it on purpose so you would see how you go off. I have a lot of times kids go off to college and they'll be like overwhelmed by the way the professor presents the material, because they're not going to go slow. They're going to go fast like that little video clip. They're going to use different terminology than I use. I try to use as much. Even when I'm talking about like acetic acid versus ethanoic acid, I try to use all kinds, but it's impossible. Everybody has their own little pet words that they want to use, their own little pet things they want to call. For example, carbocation. You look at some, the one you're going to use back here is going to call it a carbonium ion, not a carbocation. I mean, there's just different words, and you don't even know what they are, and you get overwhelmed, and then that's it. I tuned out, and I didn't learn anything from it. So let's go slowly now and tell you what he basically said about electrophilic addition. All right, fill in the blanks. Electrophilic addition is basically a 2-step reaction, okay? And here's the mechanism. First step. Here's what happens. Come on. There we go. All right. Just like he explained there, you have a double bond. That's a region of high electron density. Okay, remember, it's sharing 2 pairs of electrons. It's sharing them in a way that I never explained to you. There's a sigma bond, there's a pi bond. I never really talked about that. I didn't want to go into. I told you there's weeds that we didn't go into. There's details I didn't cover. All right, I didn't think it was important. All right, you're going to learn them in college, and they'll use those words. They'll talk about those things. All right, but it's not that big of a deal. There's a lot of electrons there. It's negative. You've got this HX up here. In the case of the video, it was a BR, but we know X stands for a halogen usually anyway. What happens in that HX is this guy is pulling the electrons a little bit more towards him. So he's slightly negative, he's slightly positive, right? Well, we know there's a lot of negatives down here. What's going to happen? That slight positive there is going to be attracted to those negatives down there, right? And the H will attach. It'll attach onto one of those guys and form, because the H, when he leaves, guess what? He leaves his electron behind. The X now looks like this. And the H didn't bring his electron with him. What did he bring with him? His proton. Yeah. So he's got a positive charge now. And that positive charge forms on the other carbon. You've added the H onto here, and you've got because the electrons that were being shared here, all right, are being paired up with the H over there. And you end up with a positive charge there because you've added a proton without the corresponding electron. He left that electron behind. So that's your first step. Let's write words that explain all this, okay? Double bonds, like I said, are regions of high electron density. Why is that doing that? Choose text color? Oh, hold on. It's driving me crazy. Double bonds are regions of high electron density. They're very negative, okay? They attract positive atoms. That first space there, all right, this is the second part here. Well, you kind of keep them together. You don't really have to have a separate dash for that. I guess I don't know why I put a different dash there. It's still part of the same word, same sense, I mean. So double bonds are regions of high electron density. They attract positive atoms or group, and we call those guys electrophiles. And if I were you, I would underline or highlight in some way electrophile. That's a word you're going to see in the worksheet and on the test. And then I would highlight or underline carbonium or carbocation. Those are words, when you watch that video, that was it. Uh-oh, there's a word I never heard before. Time for me to tune out. And that's exactly what happens to you. You can't do that. You kind of look past that. You got to try to follow something, even though the teacher's going fast. It's going to happen in college. You're not going to just get a professor who's going to take their time and go over something 20 times. The advantage you guys have that I never had, and most people who lived 20 years ago never had, or earlier, is that if you're lost, you can always look up these things. There's 1,000 tutorials out there, all right, to help explain these things when you do get to college. All right, so let's explain this now, if you all got it copied. The negative charge here attracts this positive, it's going to be slightly positive, not an ion, hydrogen here, and he attaches onto there. All right, he leaves his electron behind, so in the next step, that X, whatever he is, has a negative charge on him. He's an ion. All right, this guy's an ion too. And this is actually a very slow step because this is the one that's the hard one to do. Once you've got a positive ion here and this negative ion up here, they're going to come right together really fast. Okay? Oops. Now, here's the reason. Wait, let me go back for a second, because you'll just copy and you won't listen. All right? This is the part that explains Markovnikov's rule. When that hydrogen adds on, you can form a positive charge. You're going to have to form a positive charge on the other carbon that's next to him. Wherever that double bond is. All right? Let me draw this guy out. You don't have to do this. But wherever he is drawn out. All right? Okay, let's just take a very simple one. Okay? Like that. What would that guy's name be? One propene or just propane. Okay? Now, the thing is, when that hydrogen adds on, if he adds on to this guy right here, then the positive charge is formed on that one. If he adds on to this one, then the positive charge is formed on that one. The question is, why would he want, which one would he want to add on to? Where would that positive charge want to be? I want the positive charge to be more towards the middle because that carbonium ion is unstable. He's not happy. Anything with a charge isn't happy. And that positive charge can be better dispersed with the more carbon and alkyl groups around him. The stability of that carbocation is the key to this reaction. Okay? So write this down. The stability of the carbocation depends on the number of alkyl groups around the positive charge. Tertiary is the best. That can disperse the charge best, stabilize it best. Secondary, then primary. So that positive charge is going to be want to be formed on the most substituted carbon. Now, that's kind of weird, though, people. There's actually an old way I learned Markovnikov's rule, which I never ever taught to you guys when I first did it. All right, now I'll just mention it here in passing because it is confusing. The first step of this reaction, the hydrogen adds on to which one? The hydrogen adds on to the less substituted one. It adds on to the guy that has more H's on it. Like when I used my example a minute ago with the okay. Right. Where does the H go? Onto A, B, or C in the first step. Where does the H go?
C.
B.
Seriously, you think C? Who said C? Really? Victor? Seriously? Where does the H go? A, B, or C? The H goes on to A. Actually, you add him on here because the positive charge is formed on the other guy. So it's kind of weird. Remember, we've only been looking at the overall reaction up until now, okay, before we got to the mechanism. And in the overall reaction, we always put the group that was added, the bromine or the chlorine or the OH, on towards the middle, right? So it's kind of confusing, but the old rule used to say, for Markovnikov's rule, them that has gets, all right, to whom much is given, your increase, basically. And that's a bad way for me to, I don't like to teach it that way, but it is true. The first step of this, that's absolutely true. The guy that has more H's gets the next H anyway. All right, because that makes the positive charge more towards the middle, okay, and more towards a more substituted carbon. All right, now, and the last thing to know about this is, obviously, this is the step that's going to be slow. All right, now what does that mean? Well, that means he's the rate determining step, and that is important. I'll explain in a second.
Are you going to put this below?
There's one more dash you need to add, but there should be room there.
I don't think it's there.
Well, whatever. You put it below the little picture I've got, just as long as it's under step 1. I actually have the right number of dashes. I had the wrong spacing. Now, I'm going to use cookies as an example.
Yes. You have to.
Shania likes to cook, right? I do not have any. Okay. Let me explain how
Better go from get.
we're going to do mechanisms big time under something called kinetics, sometime in probably February. All right, January or February we'll be doing kinetics. And we're going to learn about rate determining steps a lot. Right now, I just want to mention it in passing, so you have seen it first. I'm going to do a neat little demo that's going to get that explained to you at that point. However, let me just use cookies for an example right now. Say I had to make 5 batches of cookies for Christmas. I'm making Christmas cookies, okay? Now, I want you to think about this. Each one of the batches I can make, my oven will only hold 1 tray of cookies. So each one of the batches I have to make, I could fit, I have to make 5 batches. I'm going to mix, say I'm making chocolate chip cookies. I'm going to mix my chocolate chips, make my flour, my butter, my sugar, all that stuff together, and put them in the oven. It's got to cook, it's got to bake for 15 minutes, and then I take them out. And I got to make 5 batches. Now, each one of the steps, if I broke them down into steps, adding the sugar, adding the flour, adding the adding the chocolate chips, and then baking being another step. If I do the adding of the sugar and the flour and the other stuff faster in between each of these steps, will I get my cookies cooked any faster? No, because what's the slow step in this process? The baking. It takes 15 minutes no matter what. So if while that thing's baking, I mix them up really fast, and I get them mixed up in 2 minutes instead of in just 5 minutes, does it make a difference? Because I'm just going to be waiting around anyway, right? It's going to take me 15 minutes, 5 times 15 minutes. It's going to take me an hour and 15 minutes to cook these cookies, no matter how fast I mix in my chocolate chips and my other stuff, right? The slow step in any process determines the overall rate. That's what I'm saying. You know how long it's going to take you to make those cookies, not because of how long it takes you to mix up butter and sugar and flour, but how long it takes to bake them, because baking's the slow step. In this reaction, the slow step is this first step. After this happens, that bromine that's formed, or X, bam, right on there. This step, and by the way, it's much worse than cooking. The second step, the fast step, is usually like 100 or 1,000 times faster than the first step. Okay, the slow step. By the way, the slow step's not always the first step. When we see other mechanisms in kinetics, we're going to see 1, 2, 3 steps or whatever, and the slow step's not always first. Sometimes it's second. Sometimes it's in the middle. So we're going to. That's all I want to say about it right now. I'm not going to have a lot of questions on this. All you have to know for this right now is that's the slow step. And in the next mechanism, I'm going to talk about which you think would be the slow step or the fast step. We're going to see a lot more of that in kinetics. All right. Now, the second step, really quickly. Oh, by the way, here's the first step. We can turn the light off quick. There's no noise or no sound to this one. This is just a little animation. First step, the hydrogen attaches to one of the two. Notice he went to the guy who already had hydrogens on him, and therefore forms a positive charge on the other carbon. Okay? Now, and by the way, this is also on your paper. If you can read that, I know it's very small, but it does explain to you about the different bonds and how this guy's going to be attracted, or this one's got a slight positive charge, be attracted to the negative ones here, and therefore attach X and Y. In this case, would be the H and the Br. I could ask you a question like that, right? You'd be able to explain that, yeah.
Didn't you just say that the H connects to the outside one and the center?
I didn't say outside. I said it connects to the guy with more H's, okay? The guy who has more H's. And in this case, there's no difference, okay? There's 2 H's here and 2 H's there, so it would make no difference, okay? But it would always, the H would always attach to the guy, all right, who is less substituted, so that the positive charge, the carbonium ion, the carbocation, however you want to call it, and again, there's a lot of terminology here, that guy gets the positive charge and has more alkyl groups around him. All right, and again, all of that is written out also in your notes. You can put the light back on. Now, the second step, step 2, is the fast step. What happens? This bromine, or X, or chlorine, whatever he is, attaches to that positive charge there very quickly and forms the product. All right, and he forms that product onto the guy who is more substituted. Now in this case, I've got R groups everywhere, so this is just a generic one. But anyway, so second step, the nucleophile. Oh, there's another word, another new word. I'm going to underline him. The nucleophile. Let's underline him in red. Attacks the carbocation. Now, you're going to get a lot of practice with this over the course of the next couple of days, because I've got the computers that will do this with you a little bit. Beaker will identify mechanisms and show you them as well. Not all of them won't do free radical halogenation. And I've got 2 worksheets, one probably this week and one next week as a review. It's the best I've ever covered this, best because we split it up instead of trying to jam all this into one. All right, so you should be able to understand this by the time we're done. And it seems like, again, I think I gave you in this first a taste of, because you were kind of like after free radical halogation, I thought you said it was going to be hard. I gave you a taste of how it can be hard. Okay, hold on. There's one more little thing to write down here. All right, this is the fast step. All right, and therefore, there's no real effect on the overall reaction rate. Kind of like the cookie example. If the slow step is the baking, it takes 15 minutes. It really doesn't matter if it takes you 2, 3, or 5 minutes to mix up your stuff. It's going to take you 15 minutes to bake it. And I have a little animation here, again, like silent one here for this too. You got that, everybody? Okay, hit that light. Okay, the second step then, look, I've already got my positive carbonium ion. That's the step. The whole thing's the carbocation. The bromine comes in and attaches and makes your product. Notice the bromine attaches to the guy who's got more alkyl groups around him. So here's the overall reaction. What might I ask you about this? What kind of questions I could ask you about this? I won't have them labeled. I'll ask you which is the rate determining step. Well, that's going to be the slow step. That's going to be the first step. All right. I could ask you to identify the carbonium ion. Where is the carbonium ion in this reaction? What should I circle? Circle the carbonium ion. What would it be if I had to circle it? It would be this. That would also be the carbocation, a different name. If I asked who's the electrophile, what would the answer be? The electrophile. The H. And electrophile, I want you to think about, we've used this word before, phile. What does it mean? Like. Electrophilic, hydrophobic. Remember that in biology? Okay. Philadelphia. Philadelphia is the city of what? Brotherly love. Okay, so phile or philic means pedophile. Thank you, Allie.
Abby said it first.
Abby, thank you. Right. Now, listen. So an electrophile, this is often, because of that, you often get it backwards. Electrophiles are what charge usually? Electrons are negative, right? So they're going to be positive, right? Because they're going to be attracted to electrons. Where's the nucleophile?
X.
Exactly. A nucleophile is attracted to nucleuses, which are what charge? Nucleuses have what in them? Nucleuses have what in them?
Neutron. Proton.
Oh my God, seriously? Protons and neutrons, which makes them positively charged, right? All right, so a negative bromine, whatever he is, OH, would be attracted to the positive charge here. So that would be the nucleophile, that would be the electrophile, that would be the carbocation. This would be the slow step. The second step is the fast step. This is the rate determining step. It determines the overall rate of the reaction, just like baking determines the overall rate of how fast you can make cookies. Okay?
I could really go for some cookies right now.
I could go for some cookies too. All right, that's good.